All right, so I will be talking about free-floating planets that are ejected from massive self-gravitating disks. So, as Sergei said, thankfully this has all been introduced, but I would just like to first sort of narrow our focus from talking about the general FFP population to talking about specifically Jupiter-like FFPs or JFFPs, which are free-floating planets with masses of 0.3 Jupiter masses or above. So these are the red points that you can see in this figure from Nuria's paper. As was mentioned yesterday, when you do more direct observations, you are only really probing this JFFP population. So we can only really make conclusions about FFPs in young clusters in the sort of JFFP regime. And if you were to try and sort of extrapolate down to this entire mass range that I'm talking about, Grattan et al. 2025 predicted that there are around 0.22 JFFPs per star in clusters. If we compare this to the results found by the gravitational microlensing surveys, we find that in this case, you get around 0.25 JFFPs per star in the field. So this is very interesting because, as you can see, there isn't really a statistically significant excess between these two numbers. And this tells us two very important things about the formation of JFFPs. It tells us that giant planets must form and get ejected within the lifetime of the system, so within the first few million years. And it also tells us that JFFPs likely have very low post-ejection velocities. Otherwise, we would expect them to be populating the field more rapidly than we are seeing from our observations. So how do we actually form these JFFPs early on, and how do we make them slow-moving? So you have two options, as was already mentioned by Ruth. You can form your JFFP like a star. In this case, unfortunately, we don't really know what the limit for the fragmentation is, how low down does the IMF of star formation extend down to, and also what numbers are we producing at these very low masses. It's very likely that the JFFP population as a whole is being described by a sort of interplay between these two different planet and star formation scenarios, but it's important to constrain the relative contribution of both. So instead, we are going to focus on forming our JFFPs like planets. And when you are talking about planet formation, it is very important that you specify how those planets have formed, because this will lead to a difference in the planetary architecture that you're working with, and therefore lead to very different results for planetary ejections. So I'd first like to take this opportunity to highlight this work by Coleman and Dorocco, 2025, where they were exploring how to form FFPs via core accretion. So in this case, they were modeling close binary systems. They gave the planets an N-body prescription, while the disk was given a 1D prescription that allows the planets to migrate in, which sort of facilitates these orbital crossings that cause planet-planet scattering and cause ejections. Now, the reason that they were modeling close binaries is pretty evident in the plot here. As you can see, we have the number of ejected planets on the y-axis, planet mass on the x. We go all the way down from 10 to the minus 2 Earth masses up to around a Jupiter mass. And if you focus on the red line, this is the simulations they did for a single star system. And as you can see, at low masses, you do get FFPs forming because you can sort of eject these more efficiently with planet-planet scattering. But as you increase the mass, you're really not getting any ejections at these mass ranges, unless you include the circumbinary, in which case you're still getting this planet-planet scattering occurring here, but you're also getting ejections at higher masses due to the presence of the circumbinary. So the planets can sort of migrate inwards, get ejected, and then you can get ejections at higher masses. However, you still end up not getting very many ejections as you increase the mass. This is partly due to the fact that you just get fewer planets forming in general in core accretion. So unfortunately, core accretion is able to explain the ejection of FFPs at lower masses, but it does struggle to create the JFFP population that we are talking about here. So instead, we are going to focus on gravitational instability. So in order to investigate this, we set up 3D smooth particle hydrodynamics, or SPH simulations, using the software Phantom. So we set up a gravitationally unstable disk, and we set the disk mass such that the tumor Q parameter is 1.2. So as Oliver mentioned, any Q parameter less than 1 means you're fragmenting. Over 1 means you're sort of gravitationally stable. And the reason we do this is because we don't actually want the disk to fragment. This is just an aspect of smooth particle hydrodynamic simulations. The time step is set by the density of the region that you're simulating. So very dense regions like clumps have very short time steps, which means we have excellent resolution, and that's great. But it also means that the computational costs are just far too high. It would take so long to run these simulations from first principles. So we have chosen to not do that. You can sort of get around that by giving yourself a density threshold, saying that anything above this threshold, we're going to turn into a singe particle, which is what these sort of planets are. They're post-collapse planets, and singe particles basically have no physical size, but they have a mass, and any particles that enter a sort of certain accretion radius around the singe will get accreted onto the singe and get removed from the simulation. So in this way, you don't clog up your simulation by having these really short time steps. But the issue with that is that the density threshold you're going to use is typically not really motivated by physics and is more motivated by the numerics of the simulation. If you choose a density that's too high, you're still going to get this overabundance of SPH particles, which is going to crash your simulation. But if you make it too low, you're going to be overproducing planets, which is also unphysical. This is why we've chosen to instead just insert 8 planets from 30 to 110 AU away from the host star. And we then also insert a secondary mass object with a mass that is initially from 5 to 50 Jupiter masses, but this object is allowed to grow as the simulation continues, so it's sort of like the binary seed in the simulation. It will become either a companion brown dwarf or a star, depending on how long we allow the simulation to run. So all of the simulations that I'm going to present are run for around 100,000 years, and this already takes a really long time on the cluster to simulate. Each simulation takes between a few days to 2 weeks, so that's why we chose this 100,000 years. It's also just the epoch where you get a lot of dynamical interactions and where all of the ejections seem to be occurring. And the basic principle behind this is that once you put any object into a disk, it will want to migrate. And this is an equation for the type 1 migration timescale. Type 1 migration is migration that is either inwards or outwards, so you're not opening a gap. And as you can see, in theory, this is inversely proportional to the planet mass, which means that the higher mass objects in the disk are going to rapidly migrate inwards compared to the lower mass objects, and this is what is going to facilitate these orbital crossings, which will eventually lead to ejections. Now, I say in theory, that's what this looks like, because in practice, the situation is a lot more chaotic, especially when you have a very massive self-gravitating disk like we do. So these are experiments that we ran with just a single object in the disk that is inserted into the disk at around 140 AU, which is where all of our secondaries start off at. But in this case, I've run the simulation for between 1 and 50 Jupiter masses. On the y-axis, we have the distance to the star, and here we have time. I've really cropped this figure because if I included the whole simulation, you wouldn't be able to see anything because it's such chaotic migration. But you can see that initially the objects do start migrating in differentially, so the higher mass objects want to migrate in faster. But eventually, after just 1,000 years, you're sort of getting the disk is imparting kicks to the objects, which are either inwards or outwards, which is really changing the migration behavior of all of the objects. So you can see that aside from the fact that the secondary is going to be migrating in more rapidly, the planets themselves are going to get kicked about by the disk during the simulation, which is just going to lead to a lot of interesting behavior in our simulations. But this just sort of highlights that the planet-disk interactions can have a significant effect on planetary migrations, the orbital crossings, and therefore planetary ejections. So it's very important that we simulate this when talking about GI. So this is an example of one of our simulations. This has a 50 Jupiter mass secondary. I just want to note that we are in a co-rotating frame with the secondary and the primary, so everything is going to rotate around it. And the color bar is the column density. So when I play the video, just watch out for how the secondary kicks about all the other planets. You can see it's already starting. And you can also see that just because a planet receives a kick does not mean that it's just going to get automatically ejected. In this case, actually, it kicked the planet inwards. Sometimes it kicks the planets outwards. The kick direction is basically covers the entire parameter space here. So you can get inwards, outwards kicks, and anything in between. So the story is a lot more complicated than just add big object to disk and get ejections. The planets don't really behave that way. And I'm just going to stop this here because it's getting a lot. Okay, now let's look at some more specific examples. So here I've sort of picked 3 simulations that best represent their sort of secondary mass. So we're going 10, 25, and 50 Jupiter masses. And if we look at the top panels are all the star planet distance, so the primary planet distance. The middle panel is the distance of the planets to the secondary. And the third lower panel is the eccentricity of the planets. So if we focus on the 50 Jupiter mass case first, all of these dotted lines are where ejections are occurring. And I just want to note that the time axis is sort of different on all of them. This is because it's just far easier to see. The 50 Jupiter mass secondary causes more ejections and it causes ejections earlier on. So it doesn't really need the planets to evolve a lot during the simulation to get these high eccentricities in order for them to become unbound. It's pretty efficient at kicking planets out anyway. And you can see that in the 10 Jupiter mass simulation, you're kind of getting the opposite effect. The ejections are happening later on, and they're also typically happening when the planets are already quite eccentric as a result of close encounters with the secondary, kicks from the disk, kicks from other planets. But you're basically relying on more eccentric planets in order to get ejections in the lower mass secondary case. And I would also like to highlight that we do not simulate disruptions in our simulations because we are assuming an ensemble of post-collapse planets. But if we look at the distance to the secondary, it is possible that sometimes disruptions may occur. So for example, this blue line does have a sub-AU interaction with the secondary until eventually it's kicked out. This could be a disruption, but we're not sure. At the end of the day, most of the interactions which cause significant alterations to the orbits of the planets are actually happening at around a few AU to even tens of AU. A lot of the time, at the time of ejection, the planet is quite far away from the secondary. So even these long-range kicks are able to eject the planets simply because the secondary has such a greater mass in relation to the planets. So now I'm going to look at a very specific case to show you how you can get ejections and also how you can get surviving planets in these kinds of systems, because it's not as simple as include a secondary and everything is just going to get ejected. So the object labeled number 9 is the secondary. And if we focus on the object labeled number 7 first, you can see that initially it has a close encounter. This affects its orbit, sort of forces it inwards, but it has a bit of an eccentric orbit, which sort of causes it to come into contact with the secondary again. This causes its eccentricity to increase again pretty rapidly until eventually one final kick is able to eject the planet. But if you look at the green line labeled number 5, you can see that initially it also experiences a series of close encounters, but these sort of end in the planet being kicked inwards. So even though the planet is on an eccentric orbit, eventually the secondary will stall its type 1 migration and open a gap, at which point it enters the type 2 regime and doesn't migrate inwards anymore. And this planet, despite its eccentricity, does not encounter the secondary again. And in this way, it's able to sort of survive ejection. So this is that situation a little bit more clearly. You can see that initially the planet experiences outward migration due to the disk, and then it has several close encounters, which alter not only its orbit, but also the orbit of the secondary, until eventually a final close encounter kicks the planet inwards out of the path of the secondary. And this allows it to sort of survive in the system. So another important point to bring up is how can the disk actually influence ejections? I've showed you that the disk can cause very stochastic migration, but there is also another interesting thing that can happen, which is when you get planet-driven spirals from these planets, because they're quite high-mass planets, they induce sort of spiral density waves in the surface density of the disk. And what can happen sometimes is the spiral density waves of the planets can merge, which can sort of bring the two planets closer together and facilitate a close encounter between the planets. It's important to note that planet-planet scattering does not really cause any ejections in these simulations, even when you have unequal mass planets. For example, here, the purple dot is a 1 Jupiter mass planet, the green one is a 3 Jupiter mass planet. They do not, the 3 Jupiter mass planet does not eject the 1 Jupiter mass planet. Eventually, they do move off. But what does happen is that this close encounter affects both of their orbits and causes their orbits to become more eccentric over time. So in this way, you can sort of facilitate future ejections with planet-planet interactions, but planet-planet scattering isn't really playing a dominant role. It is the interactions with the secondary that is the main driver of ejections in these disks. So here we have the ejection fraction that I get from the simulation. So on the y-axis, we have the ejection fraction. We have the initial secondary mass on the x-axis. Each secondary mass has around 3 simulations, except for the one that has no secondary mass. And the 5 Jupiter mass secondaries, these have 2 simulations each. I plotted the maximum and the minimum ejection fraction per mass, and then the shaded region is everything in between. And you can basically see that higher secondary masses do cause more ejections, but that there is also a pretty significant spread. The situation is different for every simulation that you run. So it's important to note that. But also we see that we get around 1 to 5 planets being ejected per disk. And here we have some statistics for the ejected planets. Here we have the kick velocity, so the velocity at which the planet was kicked out of the system with. On the x-axis of both plots, we have the kick location. The color bar is the initial secondary mass, and this dot dash line is the escape velocity from the system. So you can see that the planets are not really receiving very big kicks in order for ejection to occur. In some cases, it even looks like they're falling below the line. This is simply because the escape velocity assumes an eccentricity of 0, which we know is not the case pre-ejection for a lot of these planets. This is the post-ejection velocity, and you can see that it is globally pretty low for all of the planets. The average is around 1.9 kilometers a second, and we don't see any trend between the kick location and the final velocity. But what we do see is a slight trend that lower mass secondaries tend to eject planets from closer in, higher mass secondaries tend to eject them from further out. And this is the sort of main takeaway here is, are we able to distinguish between different formation mechanisms using the velocity of the planets? And the answer is yes. So the purple line, we have ejections with a secondary and a GI disk. So the work here, the average is 1.9 kilometers a second. The green line is work by Richard Parker with flybys. However, the flybys were also in GI systems, so the post-ejection velocities are again low. And here we have Coleman 2024. So he has separated the 2 lines based on whether the planet was ejected by a planet-planet scattering or whether it was ejected by the binary. With planet-planet scattering, you get higher velocities than us. And with the circumbinary ejections, you get the highest velocities. But it's important to note that around over 90% of the ejections that Coleman observed were from close encounters with the binary and not planet-planet scattering. So that's I think that this is my conclusion slide, but I'm just going to leave it here. You can read our paper on arXiv. It will be out in Munra soon. So thank you very much.
Well, thanks for the talk. I'm going to take the speaker's prerogative and ask the first question. So this scenario that you have is really appealing and you can inject lots of stuff. So to get the numbers to work and to get the right numbers of Jupiter mass free-floating planets, what fraction of systems would have to be undergoing this kind of evolution?
So not very many. As you can see, we're getting a lot of ejections. So that kind of saves us from having to have too many of these systems exist in the first place, because these are these binary systems that have final separations of around between 10 and 30 AU. You don't have to have too many of them in order to explain the numbers that we want to see.
Other questions? I see Ray over there.
No, you exactly think with like tens of Jupiter masses.
Where?
So am I not understanding the M2 correctly?
So M2 is the secondary. So these are so they're not getting ejected.
Oh, okay. So what are the typical what's the mass distribution of the ejected ones?
So for the ejected ones, they've all been given a mass of either 1 or 3 Jupiter masses, and we don't really allow them to grow, so they stay that way.
Oh, okay. So it's kind of a little bit ad hoc where you,
yeah.
Okay,
yeah.
Thanks.
So do you get this S-type orbits in this case? And what's the relation between these orbits and the binary orbit?
Sorry?
And what's the relation between these S-type orbits and the binary orbit?
What do you mean with the relation?
Are they in a specific region? They have to be stable, of course, but where they are, do you see any correlation?
Between where the binary ends up?
And the planet, the S-type planet?
No, there is the only relation for the actual final location of the binary is its mass. When it becomes massive enough to open a gap, that's where its orbit will stall. But the planets, they can either get kicked inwards, sometimes they're kicked outwards, so you do end up with a p-type, but again, those wide orbit planets are likely to be ejected from other processes. So,
and the S-types?
The S-types, they usually stay S-types, where you get just both orbiting the star. at least for the duration of these simulations. It's possible that orbital evolution will affect this later on, but we just don't simulate that.
Any other questions here? I see.
I think on slide 8, you showed the evolutions of some of the systems over time. Yeah. Maybe this is a kind of naive question, but the eccentricities for some of the planets seem to evolve kind of more in a more like chaotic sort of pattern. And then I think in the middle one, the yellow planet has this long period where it just looks like it's growing linearly. Do you have a physical explanation for that? Is there like some obvious trick I'm seeing that kind of explains that, or?
For the kind of like this weird.
Yeah, like the like weird longer linear stretches of eccentricity changes.
Sort of the way the eccentricity is being calculated, because we're looking at when is the minimum distance to the star, what's the maximum distance to the star. The kicks can sort of change that, but also the center of mass changes over time, which does affect things. Yeah, that's basically why it can look a little chaotic sometimes.
All right, cool. Well, let's thank all the speakers from the session again and go have some coffee.